Okay, so here's the thing about traffic lights. We've been using them for 150 years, and they're really terrible. I mean, really, you're going to spend about 3 months of your life sitting at red lights. I did research on this when I was doing this project. 3 months that's not really an internet hyperbole. It's actual data from a national signal data set. I'll put it up on the screen right now. But the real question isn't whether traffic lights are bad. The question is, can we actually do better? And personally speaking, I think the answer is yes, but it's really complicated. I mean, really, really complicated. The problem is, so let's talk what actually is happening here. Traffic lights optimize for the worst case scenario, which is rush hour traffic, which means they're wildly inefficient. The other 70% of the time where intersections are operating below capacity. In other words, we built our entire transportation infrastructure around peak loads that only happen twice a day. And the thing is, this isn't just about wasted time, bad enough, it's about energy dissipation. Stop and go traffic can reduce fuel economy by 40%, but it's about coordination failures across multiple intersections, creating these traveling wave effects. It's about information asymmetry. You have no idea when that light's going to change. But here's the critical point here. Traffic lights are centralized solution to what is fundamentally a distributed problem. Every vehicle is making its own decisions, but we're forcing them through this rigid centralized control mechanism. And that architectural mismatch, that's where some opportunity lies. Now, what I'm about to show you is a very huge bet, and I mean really huge. The bet is that we can replace traffic lights entirely with neural connection between autonomous vehicles. No infrastructure, no signals, just cars talking to cars, negotiating who goes when. The simulation I built demonstrates this using something called Neural Model Predictive Control, Neural MPC for short. In other words, instead of having each car run complex optimization calculations in real time, which would be computationally impossible, we train a neural network to approximate those optimal solutions. Think about it this way. Traditional MPC is like solving a complex math problem from scratch every single time. Neural MPC is like having memorized these patterns of thousands of similar problems and instantly recognizing what to do. It's the difference between calculating and pattern matching. And like pattern matching, it turns out is much, much faster. Okay, so how does this actually work? Each vehicle has to solve 4 nested problems simultaneously. First is the trajectory prediction. Where is everyone else going to be, essentially? And then second is the mechanism design. It's basically running a distributed auction for intersection access. The third is safety verification, making absolutely sure no collisions happen. And fourth is efficiency optimization, minimizing the travel time for everyone. Now, the magic happens is in the state encoding. Each car tracks its own position, velocity, and the k nearest neighbors around it. We cap k to avoid exponential growth. In other words, you only really care about cars that could actually hit you, not every car in the city. The neural network takes all this information and outputs an acceleration sequence, just a simple number between -3 and +3 meters per second squared. We then run it through a safety filter using something called control barrier functions, which means even if the neural network makes a mistake, we mathematically guarantee no collisions. Neural control is really only half the story here. The other half is priority-based intersection scheduling. The way it works is each vehicle estimates when it could arrive at the intersection earliest with maximum acceleration, the latest maximum braking. These become reservation windows. Then vehicles negotiate based on priority. Could be first come, first served, could be emergency vehicles first, could be auction based. The point is it's really flexible. In other words, instead of rigid traffic light cycles, you have dynamic negotiation between each cars. And the results are somewhat remarkable in the way the simulations I've run, at least. The simulation shows 35% higher average speeds through intersections, and a 60% reduction in waiting times, and 0 collisions and 10,000 simulation steps that I did run. So this is what I call the deployment paradox in a way. So this creates what the system requires maybe 20x more computational power than traditional control systems. So very early adopters face this really substantial coordination tax with unclear benefits until you hit like what I'd call critical mass. Probably needs about 60 to 80% autonomous vehicle penetration before the network effect really kicks in. If you're the only autonomous vehicle at an intersection full of human drivers, you can't coordinate with everyone. You're just running expensive neural networks for really no benefit at all. It's only when most vehicles can participate that the system really works here. And there is another problem, the safety requirements. Aviation demands failure rates below 10 to the power of -9 per operation. That's 1 in a billion. My simulation ran 10,000 steps with 0 collisions, which statistically gives us confidence of about 10 to the power of -4. To prove 10 to the power of -9 empirically, we need to run 3 billion intersection crossings, and that's a lot of simulation time. So now here's something nobody really talks about is this approach creates a neural moat against commoditization. Traditional traffic engineering, the formulas are public, the timing patterns are observable, but neural policies, those emerge from millions of hours of expensive simulation. You can't reverse engineer them from API calls. You can't just copy the weights and understand the logic, which means, and this is the huge bet within the huge bet, intersection management might become proprietary service rather than a public infrastructure. Imagine paying a subscription for better intersection performance. Yeah, that sounds crazy, maybe, but that's exactly the kind of business model that emerges from this sort of technology. So here's the bottom line. The simulation proves it's possible. Vehicles can coordinate without traffic lights. The efficiency gains are real. The systems will work, but, and this is a big but, possibly doesn't mean inevitable. Most intersections operate below capacity most of the time. The base rates might not justify the complexity. The network effects create a chicken and the egg deployment problem. And the tail risks, sensor failures, adversarial attacks, edge cases, those could dominate the whole safety analysis. But personally speaking, I think we could see a hybrid future, new high-density developments within the coordination-based management. Legacy infrastructure will keep traffic lights for decades, of course. The transition will be sort of gradual, if this were ever to be a thing. This is sort of just a side project of mine. I wanted to test a hypothesis, but this isn't happening. I just want to show you guys the how it works and what the project was about and everything. So, yep.